So I kind of talked about this in that one class, but I don't know how many of you were paying attention. All right. Does anybody know the distinction between a primary index and a secondary index? Yes.
Remember which is which, but one of them involves actually storing the data on this.
Exactly. So in the secondary index, you have data files, like the ones that I have given you, plus index files that, point to those, right? And index files, pages, point to data. Right? Of course, you can create many secondary indices for a given data, right? As many indices as you want. In the primary index, you have an index. In the upper level, it basically points to lower levels, right? So upper levels are the same. But at the leaf level, you actually store the data. There can only be one primary index, but you probably don't even know anything about the Highlander movie, which is kind of sad. A movie from my, college days. All right, there can only be one, whereas this can be many. I actually have been to one of the hills that Highlander actually fights in the original movie. It's pretty cool. All right, again, a movie you never know. All right, so the point is that this can be extremely fast because once you find the data that you're looking for, like we were doing the leaf scan, not only you get the key values, but you get all the other values stored in the table. Okay, but this has to be for one query that really is asked very frequently and is expensive. Because now when you're scanning the leaf nodes, you actually get all the data. It's very useful. Here, if you need attributes that are not in the index key values, you have to go and read those tuples. This is going to be an important thing. Okay? Now you can create a B tree as a primary or a secondary. Every time I tell you a B tree, you can assume it's secondary unless I explicitly tell you that this is. For example, to create this, in Postgres, you would create what's called a cluster. So to do this in Postgres, you have to create a cluster. I don't remember the exact command in Oracle, but in Oracle, this is called an index organized table, right? So in Oracle, you would look at how to do an index organized table. And the problem with this is that, for example, if you store things, but then your clusters start to break down because you now have to insert a tuple in the middle of one of the tables, but that this page is full, then you have to have overflow and you have to store it elsewhere, and then over time, this property may not be that useful because you actually are not really clustering nodes by the index value. In that case, you have to reorganize this, which is a costly thing. So if you have it very frequently accessed and changed data, this may not be feasible. But otherwise, this could be very useful. So you can only create one cluster, but can really help. But you may need to reorganize periodically. So for example, in the index that I gave you for the quiz, right, it was organized by, let's say, it was organized by student ID and section ID. That seems to make no sense, right? Because much more likely it's organized by section ID, because every semester you have a new section, you put all the students, right? So that would be a better cluster because that would be more natural to maintain, but it would only work for some queries but not for the others. So depending on what your queries are, you decide the right cluster. I'm talking about all this because when we talk about hashing, hashing is very frequently a primary index. It basically stores your data based on some value that you want to hash on. So hashing is generally a primary index. Okay. So let's say you hash on so let's see, we have students, for students, you have year, student ID. What would be a good hash for a student? I cannot think of a good hash for a student. But we can hash transcript on student ID. That will work. Okay. So what I want is I want to store the tuples for the same student ID in the same hash, as well as other student IDs that basically hash to the same value. So this is like any hash function that you find. You basically means that you basically have an attribute T of A, and you have some hash function H, and you apply that to value of A, and it will give you values, right? So it will say, the H will something, it will say 1 maps to 1, 2 maps to 2, 3 maps to 1, 4 maps to 2, 5 maps to 3. This is a great hash. 6 maps to 4, 7 maps to 3, etc. Right? So if the hash function is taking these values and mapping them to other value. Anybody's taking crypto here? You guys all know about your hashes, I assume, right? Which, this is laughable. Okay. So if too many values hash to the same thing, right? So I have, let's say, 3 things mapped to 1, right? That's called what? Collusions, right? So that means if too many things map to the same value, that means for that value I have too many tuples. Generally, a good hash has a better distribution. You use some prime number and hope for the best, but the hash function is not my concern, but there are obviously hash functions that exist that work well, so you don't have a lot of collusion. So now you have basically these values. You want to store tuples with respect to the value that they hash. So what you're going to do is, currently this hash function has only 4 values. So I'm going to create 4 disk pages. So I'm going to have 4 data pages. Okay. So this is for hash equals 1. This is hash equals 2, hash equals 3, and hash equals 4. And then the tuples with the corresponding A values, I'm going to store in these. So let's call this T1, T2, T3, T4, T5, T6, T7, and T8. So that means this page should store tuple 1 and tuple 3 and tuple 8. This hash should store tuple 2 and tuple 4. This one should store tuple 5 and tuple 7, and this one only has tuple 6. Right? So these are the actual disk pages, like a primary index, right? This is where I store all my tuples. And now I need to basically have a directory that tells me where these are stored. So this is the data pages. And then I'm going to have a directory that tells me where these pages are stored. Okay. This is the general idea of hashing. You basically divide the data using some sort of value. So in this case, it happens to be basically some hash function. Okay. And then you're going to create a directory that basically points to that. So, of course, it becomes interesting when the data that maps to, let's say, hash 1 doesn't fit in a single disk page, right? So what will you do in that case? What does any computer science do? A computer science student will know that when you have too many things, you create a linked list, right? So if page 1 for hash 1 becomes full, I'm going to have a second page, whatever it is, let's call it overflow of 1, and I'm going to put a pointer to that one at the end of my page 1. And then maybe page 2 doesn't have any overflow. If page 3 overflows, I'm going to put 1 here. And like this. So my, so here, my directory is the same, but now I have these hash trees. Because I am stubborn, I'm going to use only 4 entries for my hash. Okay? But the point is that the beauty of hash is that if you only had one node like I had before, okay, this is actually very nice because suppose I want to find a equals 4, right? Find all tuples where a is equal to 4. But what I will do is I will first apply h of 4 to find that it is actually 2. Then I'm going to go to my directory to find that h of 2 is stored in this page. Then I'm going to read this page. So generally the directory is in memory. Bless you. Then all I need to do is read this one page. And check if there is a tuple that a is equal to 4 in that page. So if I actually did not have these overflow buckets, then every single equality search is one disk access. This is not true in B trees because you have the internal nodes, right? Here, if I'm very lucky, all equality searches are one page, right? So all equality searches, one page. But it assumes that there is no overflow buckets and that the directory is in memory. What about the range search? So how about if I have a is greater than 5? How do I search for the range? It has absolutely no help. So I have to scan the whole index, right? You cannot do anything with range. You just have to search for range. You have to search everything. No help. Read all data. Okay? So it is highly optimized for equality, but not at all for this one. And hashing as a property exists in many things that we use. Google will hash keywords to farms of servers based on a hash of what the keyword is, massive hash. Anytime you run a query, there's some sort of hash. But as a way of storing data, it is challenging. Because if now you have, instead of that, all these overflows, now it may turn out that actually your searches are much more costly than if it was a B tree, because you now have, for a is equal to 1, for hash a is equal to 1, you have to scan 3 pages. So because of that, I need to have a method for resolving these conflicts. So Databases have two ways of handling this. They will say, okay, one method is the theoretician's choice. The theoreticians, of course, will always seek a beautiful but unpractical idea. So one idea is that when overflow, double the address space. Okay. So generally what you will do is you will take the hash. So your hash is some value. Let's represent that as a bit index. So let's say h of A is something like this. Okay. So if I have very few tuples, I can actually use only a few buckets. So let's say I only want to use two buckets because I don't have a lot of pages. So if I have only two buckets, I only need to distinguish between, tuples based on one bit of this. So let me take one bit of the first bit. So I'm going to have a 0 bucket and a 1 bucket. And then I'm going to look at the hash value, and if the first bit is a 0, I will put it here. And if the first bit is a 1, I will put it here. And eventually, if it starts to become full, it overflows, then I'm going to double my address space, meaning that instead of 1 bit, then I'm going to use 2 bits. So let's say that, in fact, the 1 bucket has overflown. So what I am going to do is, I am going to now create 2 new buckets. So this is going to be 0, 0, 1, 0. I'm going to have 0, 1, and 1, 1. So now, instead of the first bit, look at the first 2 bits. Okay. Now, this one was fine, so I don't really need to do anything. I'm going to simply point to the same location. But the 1, 0, I'm going to distribute now, looking at the 2 bits, to 1, 0, and 1, 1. So I'm going to distribute these to these 2 buckets. Hopefully, this is going to be like this. So this resolves the conflict. And now I can continue to have this property that everything is one disk access. And basically, if it at some point 0, 0 overflows, I don't need to actually double my thing because I can actually create a new bucket. So if this one overflows, I can just create a new one and distribute. If at some point I actually get an overflow again, then I will double my directory structure. So this is what they call extensible hashing. Now the problem in this case is that your directory is doubling every time. So your directory grows large, so it may be hard to keep this in memory. But the good thing is that everything is guaranteed to be one disk access. The other thing that you can do is do a little bit more chill. Okay, so I'll say, okay, you can have some overflows, but if in the average you don't have a lot of overflows, you can still be okay. So basically the idea is that, let's say I have the same thing 0 and 1. And I look and see overall how full these are, right? So I look at just some general fullness metric. This is becoming quite full because we actually now have an overflow. So when it becomes really full, I don't really double everything. I basically first split the first bucket. So I'm going to split this bucket to 0, 0 and 0, 1. Distribute the entries in this one between these two. and then say that, okay, currently the next bucket to be split is the 1, but otherwise you're doing fine. So I didn't really solve the problem because there's still an overflow, but eventually I'm going to come to this one and split that one too. And then when I do split that one, I'm going to create 1, 0, and 1, 1. And then I'm going to go back to the beginning because the next bucket to be split is going to be 0, 0. So I'm going to continuously go linearly in this. So every time I'm only adding one new bucket, so my directory doesn't grow as big. That means I can actually keep it in memory. But every now and then, I may actually have overflow. So this is kind of looking at, in the average, I have one access, but in practice, it may be sometimes more or less. This method is called linear hashing. This is the engineering solution. So as a computer scientist, this looks nice. If you're an engineer, you can take this one. Both of them are generally implemented, but you have to look at which database you use and how efficient their implementation is. Postgres tells you to never use hashing. You go to every single page, it says never use hashing, please. So they use hashing extensively in query processing, but not for this one. And hashing is very useful for many other things. So there are spatial data structures that are based on hashing that generalizes this. So instead of dividing the value, you can actually hash on, for example, a two-dimensional space. So for example, if this is United States, right? So this is Alaska. So you can take the United States and divide it into hashes. So you can divide to hash, you can hash in different ways, right? So there are methods to hash with respect to how much data you have. Like there are some parts of America that has no data. But there are also methods that basically divide it equally. Equally dividing is actually nice. This is like extensible hashing because you don't have to store where the bounds are, right? You can always infer it. So what you would do is you would basically store data in, let's say, 4 buckets. But then if you find that there's actually more data here, this is Northeast, you divide that more, and you find even more data here, which was, let's say maybe New York is here, right? So you divide that further and further. So you create basically an index based on the hashes of these ranges. And then you store whatever is in this box at the bucket for this one. Now, this is kind of a simplified example of what we call a quadtree. Okay? And I'm pretty certain that Google Maps is implemented as a quadtree. So you have a quadtree, meaning that when you look at Google Maps and when you go left and right, you are getting the image at that resolution of the thing to your left or to your right, right? So it's reading the image for the bucket next to you. So that it's kind of stored in something vaguely similar to this one, and quadtrees are implemented in many databases as well. Yes?
For the extensible hashing, so when we point 0, 1 to 0, 0, if we were to get something that is 0, 1, do we just ignore the 1 until the 0, 0 overflows?
Yeah. Okay. Until it overflows, exactly. So it's kind of, you're saying that I don't want to have too many disk pages that are empty, right? Because I want to be able to grab something. That's why you basically try to keep that, some property. Any other questions? All right, so let's just summarize for 1 second because I threw lots of things at you, right? So indexing is super, super crucial. Like everything I do in class, every lecture can be a class on its own, right? So there's many indexes. One thing that I want you to learn very well is B-trees, right? So generally we care about B-trees as primary, as secondary structures, but remember that they can also be primary. When we do a homework on tuning, I will want you to play with that. We will see that, okay? And then you have to realize that B-tree, while it's a great tool, doesn't solve all your problems. So I want you to know what is a inverted file. Okay. I will never ask you to create an inverted file, but if you go on an interview, you should know what it is. And you really should never have to learn R-trees for this class. But if you are interested and you will do anything with spatial data, you should learn R-trees. Okay. And then you can also figure out if for the database you use, if hashing is a recommended method, then you should learn hashing. You should at least know the distinction between the two, linear and extensible. And understand in general that what hashing does is it divides your search space. Instead of really searching something, it actually searches in a smaller one. So when we do query processing, you will see a lot of hashing because hashing is actually very important. But apparently not every database is proud of their hashing implementation. And when you're looking at inverted files, I want you to at least look at bitmaps, okay? Because bitmaps are very, very often used for queries that are not very selective, but they are becoming very important for lots of things like the JSON queries and anything that is path queries. I'll try to talk more about that if you have time. And generally speaking, hashing can also be primary. In general, any of these indices can be primary, but whenever in the exam, unless I tell you, you can always assume that I generally mean secondary. And in exams, I will never ask you a question other than B3 indices when we talk about indexing. Okay? So, any questions? Okay, so indexing is super important. It's one of the things that you have to get from this part of the class because honestly, the first decision that you're ever going to make when you develop databases is what indices to create. Okay? And to understand that, this is the thing that you have to keep in the back of your mind. And generally, if you have time, I will give you one homework where you have to figure out, given different queries that you wrote, or maybe you should have written, what indices are good indices. Okay? You're actually going to do that, and you're going to try and see if the database buys your suggestion. Okay? So we will do all of that. So I want to do like a 5-minute introduction to the next topic, but we don't have more time for that. But I want to kind of prepare you for what we are going to do next. So what we have talked about was basically a small part of a big structure that basically implements your database system. So we have seen different parts of this, but now what we are going to do is we are going to talk about how your queries are actually implemented, which will bring together everything that we have talked about in this class. Right? We talked about relational algebra, we talked about indexing, we talked about SQL, all of that will come together. Okay? And this is kind of the big, big picture. Your data is stored here, this is the sushi part, right? So you have your data, you have your indices, and you have the system catalogs that are also stored as tables that tell you where tables are stored, what attributes they have. All are stored in some file storage. Could be, multiple disks, but this is where it applies. And then on top, you have your programs, right? So your programs have basically are being executed maybe through a web browser. So you basically have your SQL, but you actually have a form that runs the SQL. You may have, people actually writing SQL, the systems programmers. You may have, beautiful systems, really high-end things like, student information system here. So you have, people who are writing programs to other interfaces like JDBC, and there are people who really do things that are really low level. System administrators will change things like how you cache and what is the size, the kernel, whatever. Okay, anytime you have an SQL, it basically first goes through an evaluation engine that compiles it, okay? And then you have to decide on many different things. So for example, you have to decide how you're going to execute this query. And that means that given a query, there are different ways to write it. Because remember, when we were learning relational algebra, there are multiple relational algebra queries that implement the same one. So the first step in our queries is to figure out what the query is, and then figure out how to implement it. Now, as it turns out, that even for a single query, like for a selection, you may have different ways that you can implement selection. So you're implementing that for the next homework, right? So you can use an index, or you can just scan the relation. These are two different ways of implementing the same query, right? So basically, you have to figure out what are the different ways. We are going to see that if you have to join, you have different ways you can join. You can do a nested loop, you can do hashing, you can do sorting, all sorts of ways. So there are many different ones. Well, the thing is that if you have many different methods, you have to figure out which one is the fastest one. That's called query optimization. To be able to do that, you have to have a model of your cost, and you have to figure out what is the right cost, and find the one that has the lowest cost. So we're going to talk about this, but we have to first understand different ways to implement it, then figure out the cost, and then find the cheapest one. Then once you know how to do it, you're going to pass it through this buffer manager that will look at different operations that you have to perform, but they will see how they can coordinate to get your query answers all at once. And the buffer manager works with the disk manager that tells you to disk get read page 1, read page 2, read page 3, so that this guy can get whatever he wants. And then, if there are people changing things, you have to figure out your transactions. You have to maintain logs or other things. And if things go badly, you have to figure out that some things have to be actually rolled back, right? When you have aborted transactions, then that's being handled over here, right? So this is the big picture. So the first thing we are going to learn is different ways to implement the same exact operation. So, we don't care about that. All right. So from this point on, you are in my world. I don't care about order of n squared. Though I did see some exam answers that were, read everything from this table, read everything from that table, in a double loop. That's not so great, because I'm trying to teach you that you can do that in one query, right? But generally speaking, order of n squared are all things that are in memory. Once you bring stuff into memory, the cost of the n squared becomes actually very small compared to bringing that stuff from memory, right? From this. So this cost is so high that we are going to disregard anything that has to do with what happens in memory. In any cases, you are not necessarily implementing that, right? Those are probably being optimized for you, let's hope. Really what we care is how many disk pages I read. From this point on, when I say what is the cost of this operation, all I care is how many disk pages I end up reading. Of course, it matters if some of those disk pages are sequential scan or random access, but for the purposes, we are going to disregard that, right? So, we are going to really care about how many pages are in a table, in a relation, and generally how many tuples there are, but we don't have this here, okay? And how much memory there is in my system to actually implement it, okay? So when we come back on Monday, we are going to talk a little bit more about this. We're going to talk about this abstract way of thinking about all query operators, and then we're going to talk about how you will implement each of them, okay? And then we'll pick up from there. So I'll see you on Monday.